Hello, my name is Chris Bale and I am the principal programmer for the Equilib interface, and I'm here with Ed Bélisle, who is the principal computer scientist at our research center. We are based at Polytechnique Montreal. This is the engineering faculty of the University of Montreal. And we're going to talk about process modeling. And this presentation is principally directed to Equilib users who want to know more about FactFlow and FactProSim and what they're about and are they useful, etc. Okay. This presentation and other documentation and links to articles, etc., is available from our website that we see at the bottom. So let's get started. There are three process modeling applications. Equilib has been around for decades. It's popular, it's powerful, it's useful, it's well liked, and it's very good for computing complex chemical equilibria. But it can be a little bit of a challenge when used in process modeling. And for example, importing or exporting streams, etc., is not that easy to do with Equilib. Users want to have calculations that are performed using a user-friendly graphical interface. So they want a process model interface. And this has led to the development of the simulator FactFlow, developed here at the CRCT by the principal programmer is the talented Kyoto Poeti. The director of the project is Professor Jean-Philippe Harvey, assisted by Kentaro, Chloe, and Professor Patrice Chartrand. So this is a homegrown process simulator. At the same time, there's another process simulator called FactProSim that has been developed offshore. The programmer is Nishan Kumar, and Maria-Lynn Van End and In-Ho Young are the principal developers. This is at Seoul National University. So why do we have two simulators? Well, the reason is the following. Okay. About 10 years ago, macro processing presentations were developed. This is the process simulation of the desulfurization of a hot metal by top slag, and it's written in macro processing. And it was developed by Maria-Lynn and In-Ho when they were working at McGill University. And they developed this interface. It's very well done, and it shows when in operation, the macro in operation, you get a display of the flow sheet, and on the left the user can interact with the system. You can dynamically enter the composition, the temperature, etc., and the macro will in real time display the plot of percentages of sulfur dissolved in the phases and so forth. If you're interested, this particular macro is stored on your computer. You can find it in the macro section in the Xstream subsection. If you do run it, make sure that your Equilib program is running as its default folder is Xstreams. Now, to set up a macro like this that performs this kind of simulation is not easy. You've got to understand macro processing, and it's not for the faint of heart. But Maria-Lynn and then succeeded, and in actual fact they also developed additional applications using macro processing, and they ended up developing this effective equilibrium reaction zone model, EERZ or EERZ, and also they then applied this to the electric arc furnace, etc. All this was using macro processing in Equilib. But there's a limit. It was so hard, so eventually they decided to drop the macro processing and develop their own FactProSim process simulation package, primarily directed to the iron and steel industry. So let us look at the options we have today with our processing systems. We're going to start off with Equilib, simulation of copper production. This is basically a simulation of the Naranda-like process, and it's a great example of high temperature pyrometallurgical processing because we have 1250 degrees Celsius, we have reactions involving a metal, a matte, a slag, a gas, and possible solids and so forth. The input to the reactor, the copper concentrate, oxygen enriched air, and silica fluxing agent. So this is directly amenable to be simulated by Equilib. The overall reactions are basically the partial oxidation of the concentrate and the dissolution of iron oxide into the slag. So these are the overall reactions approximately. You don't need to know what they are to run the program, but this is just for your information. When using Equilib for this kind of calculation, you must make sure you have the right selection of databases. And here we've chosen the FactPS, Pure Substances Database, compounds, and it's mainly for the gas. We always choose FactPS, always make sure it's included in the calculations when we use FT databases. The databases are the FT oxide for the slag and the FT mist for the matte, the sulfide phase. We could have used FT sulf, which is another database, but we'll come back to that shortly. So the overall input, as we see, is the concentrate plus oxygen enriched air plus silica flux. And the actual numbers we enter into Equilib on a kilogram basis are the following. We have 1,000 kilograms of concentrate, or a ton. We have A or alpha kilograms of oxygen enriched air. These decibels add up to 1, so A therefore becomes kilograms. In other words, if A is 100, this is equivalent to 100 kilograms of oxygen enriched air. And beta is the other variable of kilograms of flux. So these are the inputs. Let's enter them into Equilib, and this is done in the standard classical way. You Equilib reactions window, you select data search, and you define your databases, which are the FactPS, the FT oxide, and FT mist. We could have used FT sulf, which is a slightly better matte database, but our publications and our past presentations have used FT mist, and we really didn't want to change the numbers. And besides, for this particular application, it turns out that the FT sulf doesn't really make that much difference. So we're using the old one, FT mist, but should we do something new developments, then you should really use the FT sulf database. But this is the reason we stayed with the old one, because we published everything that way. Notice that the units in this calculation are particularly Celsius and kilograms. We enter our reactants in the usual manner. Note that we have 3 streams, 1, 2, and 3. It's not necessary to enter these here, but it becomes useful later on when we're evaluating the project. And may be used in the future in some of our simulations. If our reactants, initial conditions are not checked. What that means is you are not specifying the phases. We don't care about the phases because this is going to be a mass-constrained calculation. We're not interested in adiabatic reactions and the like. We see we have our 3 compound databases, our 2 solution databases, and when we're ready, we click on Next. And this gives you the classical Equilib menu window. We see a presentation of the input reactants. We see all the species collected and selected, and it's quite clear that everything's been selected. If you click on gas, then pure liquids and pure solids, this is what you get. The asterisks just show that certain species, the duplicates have been ignored. All the solutions have been selected, but select all solutions. This can be pretty dangerous. It can give you some quirky answers if you do that, but we're using Equilib to make sure that this works. And so the simple thing is to select everything, and that's what we've done. The 2 phases, COLQ and Ma2, this is for the copper liquid and the matte phase, FT mist. In FT sulf, this would be a matte phase that's immiscible with two phases with it. We have an immiscible FT oxide solution and spinel. These are the important solutions in this simulation. So we enter our final conditions. No beta 0, no silica yet. We'll do that later. And we're going to input oxygen enriched air up to 1,000 kilograms in units of 10, and this leads to 101 calculations or 101 pages of Equilib output. temperature 1250, P-bar, and so forth defined. Notice it said you shouldn't really be choosing pure liquids with these solutions. In other words, you wouldn't really normally choose pure compound liquids because they're not that important at this stage. But they've been chosen, so let's see what happens. So we're just about ready to go. There's one final item we need to look at, and that's the parameters. And the parameters enable you to control the output of the calculation. They do not affect the calculation, they do not change the numbers, but they enable you to reduce the number of lines of output in the results window. A low limit of 10 to the minus 4 is practical. Any gaseous species below that will not appear. Likewise, only the stable compounds or stable solutions will be posted. Again, that helps the output. And a third thing, which was not done, but we should have clicked on always for data source, then we could see the oxide, sulfur, mist, whatever database is being used. So next time, if we do the calculation again, we'll click on always to see the data source. So everything looks fair. We're ready to calculate. There's just one small point here, that this particular example is actually stored on your computer. You can actually access it. It's called copper without e-waste, and we'll be seeing that later on. So when we're ready to go, we click on calculate, and with great rapidity we get the Equilib results. There are 101 pages and 101 tabs, if you like, and this is tab 69, where alpha is 680. Alpha is the amount of enriched air, oxygen enriched air. This particular one value, we see the composition of the gas. We see we have 476 kilograms of matte, and we have some spinel. So this is one particular point among 101 calculations. It's just one of them. This is the fact output format. We like it because you see a gas phase at the top. It's like a furnace, and it's floating on the mat and so forth. But there's another way to present it, is the FactSage output, which is more detailed and more complete, but you get the same numbers. 476 kilograms of matte for this one particular page. So what we need to do is we need to plot this. We need to visualize it in a graph. So you click on output and you end up with the plot menu. You plot the results, and it's very straightforward to plot these results. All you do is select stable phases, and very straightforward to do it. And you end up with the phases in the kilograms and the phases, the stable phases that have been calculated. And here's one point that we just chosen arbitrarily, so you can see that's the point we calculated by Equilib, and of course we've calculated all the points along here. Now this corresponds to 0 amount of silica. One in reality would then use other amounts of silica as we try and simulate exactly what's going on in the smelting. So there would be many other diagrams we could get. So this is the diagram of the results. We point this out. There is another way to show these results, is using FactXML. This is a program that Ev has developed and written. In the graph setup, what you get is a whole slew of options. It's more detailed than the regular plotting system. You can include function builder, you can have all different types of diagrams and the like. But another factor for FactXML is you have a complete history, and you have a complete record of all the pages and all the values of the activities, partial pressures, grams, moles, everything together in tabular format. So it's useful to be able to access the calculation afterwards to get some of the details that weren't presented in the normal output. So we've done that. So now what we've done, and in this particular system we ended up using 100 kilograms of silica. So we've used Equilib, and we've calculated the matte phase here, which is the partially oxidized copper sulfide. So that's the first part. So in our simulation, we take this matte, we save it as a stream, and then we direct it to a second Equilib calculation. So this smelter is input for Equilib 2. This is the reaction that takes place, more or less. the rest of the iron sulfide gets oxidized out and we form copper sulfide white metal, and that would occur here. And again, what we would do is we now take this copper sulfide white metal, we'd save it as a stream and then import it to another Equilib calculation. So this white metal is then input to Equilib 3, where the white metal, the copper sulfide, is then oxidized to produce blister copper and SO2. So 3 steps in this simulation if using Equilib. We can plot the results we got here, and this is what it looks like. In the final step, Equilib 3, our white metal is oxidized and disappears, and our copper blister is formed, and we end up with some value up here that we would use as a result for this calculation. So you can use Equilib in this manner, but sequentially executing these tests can actually be done by macro processing, and it's not that difficult, but it's a little bit of an effort to do it. So that would be time consuming and certainly difficult to automate. You can make it general for all systems. So what we're going to do is we're going to look at our process simulation packages, FactFlow and FactProSim, at this very same operation and see how they can handle it. Now, Equilib is essential for FactFlow and FactProSim. It's a precursor, if you like. So Equilib is a precursor for these programs. Why? Well, you need Equilib to set them up. If you go to the Equilib reactants window, you can get information on your FactFlow files, which we'll be looking at. We're going to start off with FactProSim. So go to the Equilib reactant window, File, ProSim files, and it's going to give a summary of all the example files that are stored on your computer and where they are. So we'll click on that, and this is what it gives us. It gives us a summary of all the files, the Equi files that are stored in FactProSim projects Equi. Get a list of them, and you can. This is a text file that you can store. And for example, there's an Equi file, the BOF database. We can guess what that means. These are the actual input components of this BOF database. It is saved in the BOF simulation folder. We'll be looking at that later on. And you see that these are the databases associated with this Equi file. There are more Equi files here, and there's another one in the BOF simulation too, and it turns out to be the very same BOF database Equi file we have stored here. And there are other phases and other files elsewhere, and each one in all cases uses this database. Now, with every Equi file, there's a CST file, and this is where you use Equilib. A BOF database Equi file and a BOF database SysT file are coupled files. You need both of them to perform the simulation. Basically, the CST file is a mini database that contains all the data on the species and phases that you've selected in Equilib. So you take your Equilib selection, and remember we chose everything, and we can create a database that has everything in it by using the program. We'll show you how to do that. So you use Equilib to generate your CST file, and we'll show that in a second. This is for FactProSim, which we'll be looking at. This is a list of the Equi files in FactFlow. And these values in FactFlow are saved in the Equi CST flow subfolder. Equi asterisk here. And here we see the first one is the copper without e-waste Equi. And you recognize it. It's the very same system that we'd actually defined manually. And it's stored in the CST flow examples, copper without Equi. And we're going to be loading this in a moment. We see the databases that we chose. There are other examples for FactFlow on your computer. Ferrosilicium or ferrosilicon example, and here we see that. But note, this is a database of FT Light, and there's FT Steel or FS Steel, etc. So you have several examples for FactFlow, but you might not be able to run them all unless you have these databases. So we are going to look at this copper without e-waste Equi that's saved on the computer, and we're going to load it. And you load it in the usual manner. You go File, Open File, etc. Change the folder directory, and you go exactly to the CST subfolder we were just looking at. And we locate our copper without e-waste equi, and you see it selected there, and you click on it and load it as you would any Equilib file. Do that, and you end up with the very same system we entered. This system is identical to the Equilib example that we had done manually. Same system. So what we're going to do is we're going to use this equi file, but we're going to change its name because we don't want to mess around with the example stored on the system. We want to use our own. So what we're going to do is we're going to save this system, and we're going to save it in a Montreal workshop subfolder, and we're going to save it under the name copper smelting equi. So this is what we do, and this is the way we do it. We're going to click on File, and the file here, it says FactFlow Files. Save FactFlow files, equi and CST. That's what we're going to do. Just take it. So we create a new folder, and then we save the equi and the CST in it in one operation. Save equi and CST, and these will become amenable for FactFlow later on. There's another way of doing it. You can save these, plus you can run FactFlow, and Ev will be demonstrating that shortly. So we've clicked on this, we saved our equi and CST file, and of course the CST file, as we pointed out, will be used by ChemApp when we're running FactFlow or FactProSim. We're going to use the same CST file in both applications. So, just about ready to go. The next thing is to run the FactFlow simulator. One way to do it, and the simplest way, is you go to the FactSage main menu, you click on Add-ons, find FactFlow Process Simulation Package, and you're presented with this page. Help is very useful. It gives you the manual or any other information about FactFlow, and it takes you to our website. So we're going to run it. And we run it, and we get this FactFlow page. And now we're going to demonstrate FactFlow, and I call on Ev. Ev, it's up to you.
Thank you, Chris. So here we have the example that Chris showed earlier, the copper reduction example, which is open in Equilib. And I'm going to show you a live demonstration on how to do this part of the example, so the first part, in FactFlow. So let's click on File, FactFlow Files, and then we can click on Save FactFlow Files and Run. It's first gonna ask me to save the Equilib file. All right, I'm gonna replace it, and then okay, this is a good description. Okay, now the file is saved, and it created the CST file that is associated to that file, and it will open FactFlow. There we go. I'm going to keep this Equilib window here in the background open so we can refer to it. Here in FactFlow, you can see some kind of summary here at the bottom, and you can see the CST file that is here associated to this particular example that will be used here. All right, so the first thing we're going to do is set our units. So let's check what units we had here in Equilib: Celsius, bar, and kilograms. So let's do that. Bar and kilograms. All right, that's good. So let's now do our 3 inputs. So to add a new node, you just drag and drop it from the menu bar on the left. So you have 1, 2, and 3 inputs. And this is going to correspond to our 3 streams here that we had. So let's set it up exactly as we did here in Equilib. So we'll rename the first stream as feed. And this is going to be our CUFES2. Whoops. CU. Chalcopyrite. I hope I'm pronouncing this correctly. And if you're like me, and if your screen is somehow limited, you might need to move this part here to the left. You just put your mouse here and it turns into a little arrow, and you can move it so you can see the quantity here. So here we'll have 920 kilograms of chalcopyrite plus H2O. We want H2O liquid, and this one will be 80 kilograms. Here you can click on show active only. We'll clear the search window and then you can click on show active. All right, we set it up correctly. Now our second input is going to be our gas. So let's call it enriched air. There we go. And this one is going to be percentage. We'll start with 1 kilogram and then we'll adjust later. I will show you how to do that. So let's search for O2, gas. And for this one, we're going to have 43%, .24, and then we need N2 as well. Oops. And for this one, it's going to be 56.76. So this would add up to 100%. Perfect. Let's show active only. Okay, all good. And then our third input is going to be SiO2. And we're going to call this one the flux. And SiO2. We'll choose the quartz for this one, which is going to be 100% quartz. We selected relative percentage, relative quantity for this one too. But the allotrop, it doesn't matter here since we're looking at the phase assemblage only. And we're going to keep it at 0 for now to simulate what we did here in Equilib. So our 3 inputs are set up, and now we need to add our Equilib reactor. And the Equilib reactor is going to have 3 inputs. We just change this number to 3 and click on apply. And we're going to connect our 3 inputs to the Equilib reactor. There we go. Looking good. Here we have everything selected, but you could click on override here to select or deselect anything you want. Now let's set up our alpha. Like here we have in Equilib, we chose the values of alpha. So let's do the same thing, which is going to be a variable quantity of air. To do that, we click on run settings here, and we can click on new run variable. We'll call it air. And we vary this from 0 to 1000. And here it's not exactly the same as in Equilib. You have to set the number of runs. So we'll have 100 runs. If you wanted to actually start at 0 and not the first iteration, you have to click the little check mark here and set the actual start value at 0. There we go. And now we need to tell the program where to use this this run setting, this variable. So we click on our input enriched air, and here instead of 1 as the quantity, we just write down air, which is the run setting that we just the run variable, sorry, that we just entered. Air. There we go. So now we need to split whatever is going to come out of Equilib. So let's add our splitter. And this splitter is going to have 3 outputs. So let's change the number of outputs here and click on apply. Here it's a little hard to see because I'm going to add the 3 outputs. So I will de-zoom, and to do that you just scroll with your mouse wheel. You just scroll in and out, so it's pretty easy to zoom in or zoom out. So there we go. We're going to add 3 exit nodes, 1 2 3, and we're going to call them this one is going to be gas and others. So basically everything else. This one is going to be the slag. And this one is the mat. There we go. We can connect the splitter to these 3 exit nodes. And when you click on the splitter, then this is where you tell it where to to send all the components. So the split type here, we're going to select phase. We want the matte phase to go in the third output. So here we'll say we want the 100% in the third output. We want the slag to go in the second output. So here, 100% to output 2. And maybe I can move this so it's easier to see. There we go. And then everything else will go into output 1. Okay, we're almost ready to click on calculate, but we need to first, link our Equilib reactor to our splitter. And then secondly, we need to set the actual temperature and pressure where the reaction will take place. So let's set the temperature to 1250 and the pressure to 2.6, exactly as we had it here in Equilib. All right, let's click on run and cross our fingers. And we're going to calculate it at the same time in Equilib in the background. So both are calculating. Okay, so let's see what we got. Let's click on the matte and see what we got for, let's say, page 680, which is the example that Chris showed you earlier. We got 476 kilograms of matte. Let's see if we have the same thing here. So you just enter here page 68, and there we go. We have the exact same value of matte. So that means our example was successful. You can also double click here on the Equilib reactor, and you can see if you enter the same thing here, run 68, you can see exactly the same thing. So we had 680 grams of gas, and the matte has exactly the same value. If you wanted to plot this quickly, you can just select everything by using the shift key, on your keyboard. And then with just the shift key, you just click on the first one, you click on the last one, and everything is selected. And then you can click on plot. So the x-axis is going to be air. Okay. So there we go. We have everything plotted here. We can adjust the axis. Let's make this 1200. It's going to look better. There we go. And yeah, that looks pretty good. You can export the values to Excel, to a CSV file, or save the image. And the next versions, maybe in Figure as well, and other formats. We're working on this. Thank you everyone for your attention. And now Chris will show you the rest of the presentation.
Well, thank you, Ev. We just want to point out that we have enhanced our run command here just for improving the presentation. So this is the FactFlow simulator, and click on help and you get detailed information from the user manual. For example, it contains an explanation of the node palette here and all the variables along the top and so forth. So this is available anytime via the help manual. So let's return to our simulation of copper. And you recall that we used Equilib to produce the copper, 3 stages, and now we're in the process of developing the FactFlow simulation. Ev has already shown you the smelter part, and now it's simply a question of adding on the slag forming and copper mining component for the FactFlow, and you do this, and this is what you get. Equilib 1 we've already seen set up. Equilib 2 is our slag forming component, and the final one is the copper making, is Equilib 3, and this is the FactFlow simulation. Very simple to read, it's clear what's going on. You have your output matte being directed to your second reactor, being directed to your third reactor, and so forth. Crystal clear what's going on. So when you click on run, it just starts the simulation, and then when it's finished, we can look at the various components on the system. And for example, we're very much interested in what happens in the copper. making component. You click on that, and then we see in Equilib 3 the input values and the outputs. This is one particular run. We can go through all the other runs as I've showed you. Or we can plot the results, and just as I've showed you, and this is the diagram you get for this particular system. We've added labels to improve the presentation. This shows you copper sulfide white metal being oxidized to produce the copper blister. And this diagram is identical to the one we generated with Equilib, and that's what we want. So we're not just limited to copper. FactFlow can be used in a whole variety of simulations, and all these are very well documented in their article that we have highlighted up, shown on the FactSage website. For example, the primary metal production of titanium really involves 5 reactions in line, and this is very amenable to a FactFlow simulation. Notice it uses the FT-Lite database that you have available in your workshop version, but you may not have in your home 8.4 installation. This is the FactFlow simulation showing the 5 reactions taking place in line. Crystal clear what's going on, and it's simple to read, simple to understand, and a way lot better to understand than, for example, macro processing. Very well done. You click the run and you get the Equilib results, and you can trick them in the usual manner. Here's another example for the production of ferrosilicium with ferrosilicon. We have our input feed. Okay, we have our various reactions taking place. This is a recirculation in the furnace, gas cooling, and so forth. 5 Equilib reactions, and very clear by looking at it what's going on. And the final example is a ferrous example that shows the direct ion reduction in the mid-range process. Again, 5 components taking place, and again, well documented in the articles. So, we've used FactFlow. Just finally, and we were asked to present this to show you that additional information, and this is too complicated to present in detail now, but just to point out that FactFlow has a dedicated analysis module. You can have custom variables defined by graphicals. You have a function builder, and you have a whole slew of way of defining runs and iterations and what have you. So this is documented elsewhere. So much for FactFlow. Let us look at FactProSim. And in many ways, FactProSim is run and operated just like FactFlow. So you go to your FactSage main menu, you click on add-ons, and I would just like to point out here that with add-ons, there are Equilib add-ons available. What does that mean? It means, as you see behind you, if you were to click on Equilib, you can only run Equilib at once. The Equilib button then goes into, is disabled. But with Equilib instances, you can actually enter up to 4 Equilib reactions. You can do 4 Equilib calculations simultaneously that are completely independent. For example, you might have one Equilib calculation running in the background that's heavy duty, that takes hours and hours, and you might have other Equilib calculations that are short term, as you wish. But that is available, and it's not used that much, but it's very worthwhile checking out. Anyway, getting back to our FactProSim, we click on the ProSim package at the bottom. We end up with the options here. Help will give you information on the manual, but we're going to click on Run, and we end up with the FactProSim simulator. Click on Help, and it shows you what the buttons are used for. Quite similar in presentation to FactFlow. We have our modules panel, the nodes that were in FactFlow, and we have other options there. So these are well documented and listed here. And we see along the top our options and buttons that are very clear and quite detailed and well. So we are going to be simulating the copper smelting. We're going to use exactly the same copper smelting CST that we generated with FactFlow. So if you just copy this and put it in the FactProSim workshop, then you're ready to go. Or you can generate it from the beginning as I did with FactFlow. So we need to then tell the program to load the CST. So we CST load this value, okay. And we need to save the project as a .ppf file, copper smelting ppf. Okay, so we're ready to go. Click on ready. Now we're going to make it entries for the copper simulation. Pretty similar to what we saw in FactFlow. You drag and drop an input stream, and you end up doing it 3 times. You end up with 3 input streams. You drag and drop the Equilib reactor, and likewise for the output streams, just as we showed with FactFlow. Now it becomes a question of populating the streams. And for example, if we click on Enrich there, we get this nice window that shows us the options and how we can define the species and so forth. It's very clear and it's very well done. Input amount and so forth. We can also define our Equilib in a similar manner, species and phase selection, etc. And we can do the like for the output streams and so forth. So it is possible to construct the whole simulation, FactProSim simulation, and it looks like this, and it's set up this way. And so you can then see with this 3 Equilibs, Equilib 1, Equilib 2, Equilib 3, just like we saw in the Equilib simulation, just like we saw in the FactFlow simulation. They're very similar. So when it's all set up and run and everything, you click on Run. The simulation takes place, and what happens is you get the results directed to the copper component. Click there. Unlike FactFlow, FactProSim tends to sort of produce the output in an Excel format that you can then address and produce diagrams from. So very detailed Excel spreadsheets are produced with FactProSim, and you can plot whatever you want. This is the copper diagram. Okay, so the thing is that with FactProSim, it's not really directed to copper, it's more directed to the iron and steel industry. And for example, the simulation of aluminum addition to a label or the desulfurization of a hot metal, we've already seen that with the macro processing. Somewhat. Simulation of BOF or BOF with combustion and heat recovery. The point is that these examples are very detailed, and they're for complex industrial processes, basically in the iron and steel industry, and some may use this effective equilibrium reaction zone, the EERZ or ERZ model approach. All the examples you have use the same databases as we see there. So let's try one out. This is simulation of the BOF process. This is just a schematic of what's going on, and these are typical amounts of input of the phase and slag and so forth, and there's a kinetic aspect to it, and there's a limit time and so forth, adiabatic conditions. So it's pretty detailed in how you set it up, and you'll see a spreadsheet, Excel spreadsheet in a moment. This is the actual flow sheet that we need to generate, and there are certain kinetic factors involved. And if you translate this into a FactProSim simulation, that's what you get. And see, we have our 3 components, hot metal. We have a splitter that gives you reacting and non-reacting stream. This is for kinetic purposes. This is well documented though. We have our 3 Equilibs taking place, and eventually we produce our hot metal. So this is the classical BF process that they show. They've also enhanced it with the post-combustion and heat recovery options in the flow sheet. Now this is getting pretty detailed. I won't even begin to explain how it works. Okay, but it's very well done, very detailed, and clearly you could not do this with microprocessing. It'd be impossible, but you can do it with the FactProSim. In this particular case, this is the FactProSim flow sheet that you get. Again, it now includes the heat exchangers and the final production. To run this, you need to put in input data from an Excel spreadsheet, compositions and the like, time modules or time steps, amounts added, and all sorts of stuff you can put in to improve the simulation. And eventually, when you say calculate, you get a whole slew of Excel spreadsheets results. This is the this is the FE liquid that's produced, and we're plotting some of the conditions. Or this is an example of comparison between the VOF simulation standard and the BOF simulation with the heat exchangers. We had both, and you see the plotting of the temperature of the profiles are quite different, but you have similar compositions. for the carbon and silicon. So they wanted us to point this out. It's too detailed to go into details, but just to indicate that you can have simulation of batch processes, you can create custom equations, and you can use the ERZ model approach. You can look these details up later yourself. But the important thing about FactProSim was developed primarily for the steel making industry. There's a consortium of some 14 industrial partners. It is supported right now. It's continuing to be developed. And what they're trying to do is get more user-friendly graphical outputs, and they're working on that right now. So this is the FactProSim summary. So we're almost complete now. Let's look at both processes. This is a comparison. So both FactFlow and FactProSim give you a beautiful graphical interface that's very readable. You know what's going on there. You know that you're getting reactions and so forth, and you can see it's done the same way. I program in both, and I found out that once I have my flow sheet defined, and then I enter, for example, in FactFlow to have the simulation, my entries into FactProSim to do the same situation are pretty much the same. They're virtually identical. They're different terms and stuff, but it's the same concepts, input and output and directing a stream. It's a question of getting all your streams and all your components right and the amounts you need to add. That's the hard part. It's specified exactly what are your inputs for the input streams. That's the difficult part. But the rest is fairly straightforward. Here, for example, we see two output streams. One of them is, in the case of FactFlow, gases and others. And this is the copper blister. Down here, this is the copper blister, but we separated the gases from the others. So it's the same simulation. For a great pleasure working with both. Fun to work with both. And as someone who, since I developed the Equilib interface, and I also developed the microprocessing, I really appreciate this output of using Equilib in a much more meaningful manner for process simulation. It's a pleasure to work with it, and these are great processing algorithms. So, as a summary, FactFlow and FactProSim packages, we've already seen this. They're developed for user-friendly graphical interfaces. They access the same databases, and they employ the same Gibbs energy minimization, and they calculate the same results. And you get the same values, obviously. But they do have different applications and uses. FactFlow is really designed for users who want to extend the Equilib experience with streams and stuff. For example, Equilib is really useful for simulating high-temperature pyroanalytic processes under equilibrium conditions. It's very well suited to do that. FactProSim is a more detailed application, really designed for the steel-making industry, and for example, the simulation of additions to ladles, desulfurization of hot metal, VOF process, and so forth. And it's associated with the ERZ, or the model approach. Very powerful, very detailed, very powerful, very interesting. I love using both, and I hope both succeed. So, I wish to thank you. Evan and I wish to thank you. We appreciate you watching and listening to us. For more information on the process simulations and the details of the packages and articles and so forth, please visit our website. Go there directly, and we appreciate your presence, and we're ready now to answer your questions.